All right, last section here. We're going to talk about spontaneity, like spontaneous reactions and the driving forces, things that cause things to happen. But what does it mean to be spontaneous? Let's first go there. So for a chemical reaction or a process to be spontaneous, what that actually means is that once it gets going, you don't need to help it along. All right, so it doesn't necessarily mean it's just going to happen instantly. A lot of these things, they need like a little nudge to get going. So think of it like having a bowling ball on a hill, but it's like sitting on like a speed bump or something. So it's kind of like hung up on the speed bump there, but if you push it over that speed bump, then voof, then it's just gonna like roll down that hill spontaneously. But until you knock it over that little bump, it's just gonna chill out there. So lots of reactions are like that. There's something called an activation energy. But once it gets going, it's keeps going. You don't need to keep on pushing it along there. So let's talk about spontaneous things and try to figure out like why some things are spontaneous. All right. A huge number of reactions are exothermic. In fact, most spontaneous things are exothermic. So the products are more stable than the reactants. And there's a definite tendency of nature to lower the energy, so to move to a lower energy state. All right, but not all spontaneous reactions are exothermic. There are some things that are endothermic that will happen all on their own. If I take an ice cube and I bring it out and I put it on the table right next to me, right now in this room as I'm recording this, it's going to start melting. All right, just spontaneously. I'm not going to have to help it along. It's going to melt. All right, when ice melts, is that endothermic or exothermic? Right, heat has to go into the ice to melt it. So that's an endothermic process that's happening all on its own. So enthalpy is not the only player here. There's something else going on. All right. The other thing is called entropy. Right? It's the chaos. It's the disorder, randomness. And it's related to the various modes of motion of the molecules. They can wiggle, waggle, rotate, move from place to place. All this crazy stuff. That's all the chaos. So yeah, the symbol for entropy is S. It's like, I know, I have to apologize on behalf of all science because this is getting kind of crazy now. So entropy is S. Heat energy was Q. Enthalpy is H. So yeah, why not? Let's just make this S. But there is truly a driving force for chaos, all right? Like for things to just kind of naturally order that. I mean, it can happen. There are, like, I'm not going to go into it here, but there is a driving force for chaos. Like if you're putting your clothes away, let's say you have a dresser and you have it organized where your socks are on the top drawer, then you have shirts and pants. You're not just going to go in your room and hurl your clothes in the air and then have them land in the drawers all folded up neatly. Like, it's not going to happen. I have a hard time even thinking that's possible to happen. But let's go to something else, like a handful of coins, like a big handful of loose change. You have pennies, nickels, dimes, quarters, and you just throw them against the wall. Like, what are the odds that it's going to land with all the pennies in a stack, all the nickels in a stack, all the dimes in a stack, all the quarters in a stack? Like, is that even possible? Yeah, it's possible. Like, they can bounce off the wall. They could land there. But it's like super duper ridiculously improbable. All right, it's not very probable for that to happen. That's because of this chaos, this entropy, this driving force of just disorder. All right. The entropy of the universe is always increasing, and so in any spontaneous process, it's going to increase the entropy of the universe. This is also known as the second law of thermodynamics. All right, and the guy who did a lot of work on entropy was Ludwig Boltzmann. All right, so here's his tombstone. Pretty cool looking guy here. So here's entropy. This is called the Boltzmann constant. So you know you're cool when you have a constant named after you. So the Boltzmann constant, this is W, so microstates. Don't worry about that. But when I first saw Boltzmann, I was like, he looks kind of familiar. This is Kerry King from Slayer, an old metal band that's actually still kicking around. Look at them both. I think Ludwig Boltzmann and Kerry King are the same person. Like Boltzmann's he's a warlock or something, and now he plays in a metal band. But I'm all distracted now. So let me get back to science. All right, so what you guys need to know is that entropy increases with temperature, it increases with volume, and it's going to increase with the number of independently moving molecules or particles, right? Just think about temperature. When you heat things up, right, at low temperature, there's a distribution of speeds, right? It's kind of like that, had that big peak on it. But when you heat it up, you get this big, broad distribution of speed. There's lots of different speeds, lots of things, lots more collisions, lots more chaos, things moving fast, things moving all over the place. Volume, kind of self-explanatory. Imagine you're like babysitting some kids. You have them all in one room. That's fine. Now they're free to roam the whole house and the property and the whole neighborhood. You're going to have a hard time keeping track of them. Lots of chaos. Right? So the more volume you have, the more places things can be, the more chaos. And going back to our babysitting analogy here, like watching one kid, now you're watching 50 kids. Like imagine watching 50 toddlers or something and just no. All right, the more stuff you have, the more chaos. All right, that's easy enough. What about states? States of matter. What do you think the most chaotic state of matter is? What do you think the least chaotic state of matter is? If you thought that, hey, a solid is the most ordered state of matter, then you are correct. And then as we go to liquid, there's more entropy, and then go to gas, that has the most entropy, right? The most craziness. There is a third law of thermodynamics. All right, it says that the entropy of a pure crystalline substance at absolute zero is zero. There is no disorder. Things aren't even wiggling. All right, so at absolute zero, there's no motion at all. There's no vibration. Everything is perfectly ordered. It's in its perfect place. As you start warming it up, things vibrate, things wiggle, things get out of whack. All right. Because of this, though, they can actually calculate entropy for lots of different substances. We don't do it in this class, but in AP Chem, like we do some calculations where we use big tables of entropy and fiddle with it. All right, I'm going to show you one last equation here. All right, we're getting there. Ah, yes, delta G equals delta H minus T delta S. This is called Gibbs free energy. All right, this kind of connects the enthalpy and the entropy. So these are the two things that actually give us energy. So there's the enthalpy part and there's the entropy part. So the heat part and the chaos part. Kind of weird, but eventually it'll make more sense. So we have this enthalpy term up front, and then this is the entropy term. This, like, it might look crazy, but what we're going to do with this is just figure out if a reaction is spontaneous or non-spontaneous, all right, based on the sign of delta G. If delta G is negative, it's a spontaneous reaction or a spontaneous process. If delta G is positive, that means it's non-spontaneous. That means it's not going to happen, without you pushing it along. All right, so how does delta G change with temp? I want to do a bunch of these in class. We'll fiddle around with them. But this equation does show us how some things can be spontaneous at one temperature and then non-spontaneous at other temperatures. So just for a really quick example, let's talk about something that's exothermic. So if it's exothermic, what is the sign of delta H? It's negative, right? So let's do something that's exothermic where the chaos is increasing, where my entropy is increasing. So if the entropy is increasing, delta S is positive. So exothermic, negative. So if I take a negative number and I subtract a positive number, it gets more negative. So something like that would be always spontaneous. All right. So there's never going to be a temperature where it's not going to be spontaneous. It's always going to be spontaneous. And this is our Kelvin temperature, by the way. So this is never negative. All right, we'll do more of those in class, but I'm going to wrap that up right now. That is actually the end of chapter 15. Yeehaw, you made it. All right, see you in the next chapter.